Hello! Remember when I introduced the time axis as ct to measure distance and time with the same unit? Well, in relativity we can measure distance in meters and time in seconds, but we can also measure distance in meters and time in meters. When you multiply ct, you are getting units of distance, so you can measure time in meters. But we can do the opposite. We can measure time in seconds and distance in x over c, which gives you seconds. So yes, we can also measure time in seconds and distance in seconds, which would be the time that light needs to travel that particular distance, also known as light seconds, for example. In this lesson, I am going to use t for time and x over c for distance, so I will measure both of them in seconds. Now, consider the following. Two Daleks, evil creatures whose only goal in life is to are traveling in a fast train. The train moves at 60% of the speed of light in the positive x-axis when it enters into a tunnel. One of the Daleks is ahead in the train and the other is behind in the train. You, at rest in a tunnel, measure that the distance between the two Daleks is 80 nanoseconds. Remember that in this lesson I am measuring space distance in seconds, or nanoseconds in this case. When their clocks tick, they both simultaneously, in the train reference frame, they shoot their gun stick perpendicular to the train, leaving two holes in the tunnel. We will call these two shots event A and event B. We define one of the holes as x prime equals to 0. What is the distance that the Daleks measure between the two holes? Well, if you in the tunnel measure that both Daleks are separated by a distance of 80 nanoseconds, and because of length contraction, this means that in the Daleks reference frame, they are separated by L0 equal to L times gamma. Gamma for a beta of 0.6 is 1.25, so the Daleks are 100 nanoseconds apart from their reference frame. Now, what is the distance between the two holes as seen from the tunnel? Can you guess what the answer is? Let's do it properly. Let's use Lorentz transformation equations. We know that the coordinates of events B and A from the train's reference frame are x prime A equals to 0 and x prime B equals to 100 nanoseconds. Also, t prime A equal to 0 and t prime B equal to 0. Using Lorentz equations, we get that xa is equal to gamma times x prime A plus v times t prime A. xb prime is equals to gamma times x prime B plus v times t prime B. Now we subtract one from the other and get that xb minus xa is equal to gamma times x prime b, which is 1.25 times 100 nanoseconds. This is 125 nanoseconds. So how is it possible that from the tunnel reference frame both Daleks are separated by 80 nanoseconds, but the holes are separated by 125 nanoseconds?
What have we missed?
Yeah, what did we miss? Well, let's complete. To use Lorentz transformation equations, let's calculate the times TA and TB as seen from the tunnel reference frame. TA is equal to gamma times T prime A plus x prime A times v over c squared, which is 0, and tb is equals to gamma times t prime b plus x prime b times v over c squared, which is gamma times x prime over c times v over c. This is 75 nanoseconds. Remember here that beta is v over c, and I am using units of distance as x over c. So both shots are separated in time by 75 nanoseconds, as seen from the tunnel. Both shots are not simultaneous. So even though the Daleks are separated by 80 nanoseconds, because the Dalek at the back of the train shoots first and the Dalek at the front of the train shoots later, meanwhile the train has moved. Actually, it has moved b times delta t, which is 0.6 times 75. That is a distance of 45 nanoseconds. So the distance between both holes is the contracted distance between both Daleks, 80, plus the distance traveled by the train between shots, which is 45. 80 plus 45 is 125.
Oh, yes.